Hello, everyone. After reviewing the arrays, linked list, stack, and queue data structures, in this lecture, we will just have a quick review of tree and graph data structures. Okay. So the difference between the previous data structures we studied and the tree and graph data structures is that in arrays, linked lists, trees, in arrays, linked lists, stacks, and queues, so these are one-dimensional data structures, which means when you are talking about an array or a linked list, the item is on the next or previous of the current one. So that's just like a linear sequence. So there is only the next items and the previous items. And stacks and queues are built up in the arrays and linked lists. So they have the one-dimensional structure. However, with the trees and graphs, so these are hierarchical data structures, and actually they represent a relationship between the items. So those relationships can be many different types. So that is why with the tree and graph data structures, we call them the hierarchical data structures. In other words, actually, a tree is also a graph, so it's just an undirected connected graph without a cycle. Okay, so let's start with the tree data structure. With the tree data structure, actually, we are implementing a parent-child relationship between the items. Usually, when we talk about trees, those are rooted trees. Okay, so rooted trees means one of the nodes in the tree is my root node. For instance, in this tree on the left, this is the root node. And the items in this tree represent a parent-child relationship. So this root node, which has a value of 2, is the parent of its children. So 7 and 5. So 7 and 5 are the children of root 2, and root 2 is the parent of 7 and 5. Yet another example for this node 7. So who are the children of 7? 2, 10, and 6 are the children of 7. Who is the parent of 4? The parent of 4 is 9. Okay, so this is called a tree. And in a tree, there are no cycles. There are no cycles, which means if you would like to go to a node in the tree, starting from the root, there is only one path leading you to that node. For instance, if you would like to go to 6, starting from the root, this is the only path you can go there. Okay, so there is no other. Okay, so there are a lot of terminology regarding the tree data structure. Here are some of them. Siblings. Okay. So 7 and 5, they have the same parent, so that makes them siblings. So what is an internal node? In an internal node means this node has at least one child. Okay. So for instance, 7 is an internal node. It has 3 children. 5 is an internal node. It has one child. 9 is an internal node. It has one child. 6 is an internal node. It has 2 children. However, these nodes, 2, 10, 5, 11, 4, these do not have any children. So that makes them external nodes or the leaf nodes. What else we have? So ancestor and descendants. Okay, so let's consider node 9. Okay, so who are the ancestors of node 9? So who are the parents? That means starting from the root, if you travel to node 9, the nodes that you pass through are the ancestors of 9. Okay, so to go from 2 to 9, I should go to 5, and then from 5 to 9. So that makes 5 and 2 ancestors of this node 9. Similarly, who are the descendants? So they are all the nodes just below this node who have this node as their ancestor. So let's say for 7, you can go to 2, you can go to 9, you can go to 6. All of these guys have 7 as their ancestor, right? Similarly, 5 and 11. So these all have this node 7 as their ancestor. In other words, if you would like to find the descendants of a node, you may just assume a subtree from that node and consider all the items in this subtree. Okay, what else? There is the edge and path. So every connection connecting two nodes in the tree, it's called an edge. So this is an edge, this is an edge, this is an edge, this is an edge, right? And a path is always unique in trees, which means you start from one node and you go to another one. If there is a path, then it is always unique. You start from, let's say, from 7, and you would like to go to 5. So from 7, you can go to 6, and from 6, you can go to 5. So this is the path from node 7 to node 5. As I said, in a tree, all the paths between two nodes should be unique. Why? Because trees, they do not have any cycles. Okay. Good. Usually in the algorithm design and analysis, the depth and height of a tree makes sense. So that is why we need to define what is the depth of a node and the height of a node. First, let's start with the depth of a node. It is the number of ancestors to the root, but excluding itself. So assume I'm considering node 6. Okay, so what is the depth of 6? That means starting from the root node, how many edges will I pass through to reach that node? Okay, so this is the first and this is the second, right? So you pass through the two levels to reach node 6. However, the depth of this one, that is why we call the depth of node 6 is equal to 2. In other words, if you follow the reverse manner, so you will say that, okay, so I will go to my parents, so that is 7, that makes 1, and then from 7 to 2, that makes the second. Okay, so that is the depth of a node. Let's do another example. So what is the depth of 11? So 1, right, and then 2, right, and then 3. Okay, so that is the depth of 11. This is the depth of node 11, and then when you talk about the depth of a tree, it is the node with the maximum depth. Okay, so since we do not have any nodes in this tree that has a depth greater than 3, so the depth of this tree is also 3. In the same way, the height of a node is its distance to a leaf. Okay, so I would like to find the height of node 5. That means instead of traveling upwards towards the root, I will go downwards to a leaf node. Okay, and then I will write the descendants. Okay, so this is the first descendant, and this is the second descendant, and then I reach the leaf node. So that means the height of this one is equal to 2. Okay. Then what is the height of 7? Because I can go to a leaf node with just one edge, or I can go to a leaf node with 2 edges, either here or here, right? That is why when you have more than one option to reach a leaf node from an internal node, the height of this node is the longest one. So we say that. So this node has a height of 2. Okay. Similarly, the height of a tree is the maximum height its root node has. Okay, so for this root node, actually you can reach the leaf in just 2 steps, right? Or you can reach a leaf node in 3 steps here, 3 steps here, 3 steps here. So that makes sense. We will always be considering the longest path. So we will say that the height of this tree is equal to the height of its root node, and it is equal to 3 in our case. Okay. Binary tree has a special position, has a special emphasis when we are studying the trees. So let's go back to the previous one. So what is an n-ary tree? Maybe we should first consider that. Okay, so if we say n-ary tree, so that n is the maximum number of children an internal node can have. If I say this is a 4-ary tree, that means there might be some nodes in this tree that can have 1, 2, 3, 4 children. That is why when we say the binary tree, actually this is a 2-ary tree, and each node can have at most 2 children. Okay. And these binary trees are of exceptional importance because in algorithms, when we start studying the algorithms, we will see that they make a lot of sense in many of the algorithm design as primitive blocks. So that is why usually we study the binary trees in data structures with a special emphasis. And in this course, we will have later more detailed, more sophisticated lectures regarding different types of trees, and we'll be visiting those binary trees again. But just to remember what they were, so this is a tree, and each node has at most 2 children. If each node has either 0 children, no children, or the maximum number 2 children, so then that means this is a proper binary tree. For instance, this tree is not a proper binary tree. Why? Because, for instance, that node has only 1 children. However, to be a proper binary tree, each node should have 0 or 2 children. So that is why this tree is not a proper binary tree. However, if we consider this subtree, so can we say that this is a proper binary tree? So let's see. So this is my root node and it has 2 children, and that is fine, okay? So for this node, there are no children, so that is fine. And for this node, it has 2 children, which is fine. And for those leaf nodes, they don't have any children, so these are all fine. That means this part of the tree, this subtree, is a proper binary tree. And there are many properties of those binary trees, and it might be good to remember them by checking our textbook. Okay, as I said, this course is not a data structures course, so we are just remembering our previous knowledge, not going into the details of those data structures. It is also important to remember how we implement the trees. Again, there are two ways you can implement binary trees, either by using a linked list or an array-based representation. So let's first focus on this linked list-based implementation. Okay, so let me see if I can make it great. Okay, good, much better. Okay. For each node, what I need is a parent link. Okay, so each node's parent should be connected to that node, unless it is the root node. And each node has a number of children. The number of children, that is a variable number. So that is why in this implementation, so we have another node that has the pointers to all children. That means this specific node has 1, 2, 3, 4 children, and where they are, you should follow the corresponding links. Okay, so parent pointer, children's pointer, and then what is the actual data in this point? So it is also another value. In this example, it's just names of the cities. So for each node, very simply, so this is the parent, this is the child, and this is the own data pointers. You can just create a linked list in this way, which will implement a tree. Okay. What else can we do? We can use some array-based implementations. Actually, so for those implementations, I suggest you to just check some different representations on the you can find on the internet. So LOD, balanced parentheses representation, those are all array-based implementations, but they are used to implement trees in a more sophisticated way, particularly to implement a general tree, a general n- ary tree. But once we have a binary tree, then the array-based implementation of the binary trees, so that is more interesting because we can just make it with a simple calculation. So we can say that, okay, so I will just place the root at the position, at the initial position. So let's say we have here a zero-based array. So the first element of this array is the root, and I will place its left child to the position 2 times current position plus 1, and right child 2 times current position plus 2. 2 times 0 plus 1 gives me this position, right? So at this position, I will put the left child, okay, 7. And 2 times 0 plus 2 is equal to 2. So that is why I will put the right child to the position 2. Okay, so this is the right child. Good. Then how about the left and right child of 7? Okay, so 7 is at position 1. 2 times 1 is equal to 2, plus 1 is equal to 3. At position 3, I will accommodate the left child of 7, which is 2. And at position 4, why? Because 2 times 1 is equal to 2, plus 2 is equal to 4. So that makes 6. So this is the right child of 7. Good. We are done with 7. So let's go and check 9. So what is the position reserved for the left child of 9. 9 is stored at position 2. So that makes 2 times 2 plus 1, which makes 5. 5 is reserved for the left child of 9. Since 9 does not have a left child, we leave it empty. Okay. And what is the right child? 2 times 2 plus 2, position 6. Okay. And position 6, I will have this other value 9 there. Okay. And in this way, you can just fill the array. But the point here is, if the tree is not a complete binary tree, which means all the nodes have either 2 children or nothing, okay, then this means you might have some gaps in the array implementation. Such problems are the ones that we will be dealing in the upcoming lectures, maybe. Okay, but these are some efficiency issues. Okay, good. So that's the implementation. What else we can remember about tree data structure? Surely the tree traversal. So we have 2 types of traversals. We have the breadth-first traversals and we have the depth-first traversals. And for the depth-first traversals, we have the pre-order and post-order traversals. In addition, if this is a binary tree, you can also have an in-order traversal. Okay. So let's quickly review those ones. We start with the breadth-first traversal. So breadth-first means level by level traversal of this tree. So this is the first level, okay? And then this is the second level, third level, and this is the fourth level, right? So that is why actually what I want to do is I would like to first have this one here, and then these 2 guys to appear here, and then these 4 guys to appear here, right? And then we will have the rest appearing next. Okay, so this is what I want at the end, and how I can achieve it is by the queue data structure. Here you see the pseudocode of a breadth-first search. Okay, so these are taken from this book. If you would like to check that book, very welcome for sure. Okay, and with the breadth-first, what it says, we first initialize a queue that contains only the root node. So this is my root node. So I create a queue. This is my queue, and I in-queue the root node. What else? Nothing. Okay. Once I have this queue initialized, I will start. First, I will dequeue from this queue, which means I will get the first item that has been inserted into this queue. What is it? It is the root node itself. So I dequeue and print it. Okay. So once I print it, I dequeue. So this is gone. Okay. When you have this node fetched from the queue, what I will do is I will go to that node and in-queue its children into the queue. So who are the children of this node that I just fetched, extracted from the queue? They are these nodes. That is why I in-queue the multiplication operand and the addition operand to this queue. Okay. So what I did, I'm now inside this while loop. I dequeue the item. Perform visit means I have printed it, okay? And then for each child of this one, I perform the enqueue operation. What I will do, I will repeat the while. Okay, so now, who is the first item to get service in the queue? It is this multiplication operand. So that is taken out. So okay, it's gone. Okay, so that means now we have the addition operation at the top of this queue, but it is still in the queue. But this for multiplicand operand, so it is fetched from the queue and it is printed. What I will do, I will run this for loop for this multiplication operand. So who are the children of this multiplication operand? These are its children. So that is why we enqueue them to the queue. Done. Again, we go to the beginning of the while loop. Who is there? I have this item. I will get this out and print it here. Ready? Okay. And now is shifted to the left by 1. Oh, sorry. Oops. I will just be moving these ones. Here it is there. Right here, right? And I will enqueue the children of these guys. That will be 3, and this will be 1. And this will go in this one. Okay, so you got the story. But at the end, by using this queue, you will have created the breadth-first traversal of this tree. What I strongly suggest you is to try this traversal on a general tree without using a queue data structure. So you will see that it will be quite difficult, and that is why this is a very nice example of how queue data structure helps us in a difficult problem, okay? Again, going back to our previous discussions, a data structure is something that helps us on the task that we would like to achieve. In this example, I would like to have a breadth-first traversal, and the queue data structure helps me a lot in this journey. Without this queue data structure, can't I do that? No, I can do it, but this will be a lot more difficult. Okay, so that was the breadth first, and for the depth first traversals, so we have those pre-order and post-order cases, and if the tree is a binary tree, we also have this in-order traversal. Okay, so let's start with the pre-order. On all of these pre-order, post-order, and in-order traversal, we will be using a recursive algorithm, which means this algorithm will be calling itself again and again. Okay, so let's start with the pre-order. So pre-order says, first, perform the visit action. For the visit action, I will just use print it to the screen, okay? And then once you visit this node, print this node, what you will do is you will call the same function for all of its children. Okay. When will it stop? So when a node is a leaf node, an external node, and it does not have any children, then this means there will be no more recursions forked. So the recursion will end at that position. So let's do it. Okay. So I start with the root node. Okay. So root node, and then this will call itself for the first child of this root node, which is this one. So you have printed this division operation and then the multiplication operation. You go there, you print the addition, you go there, you print 3. And since 3 is a leaf node, it doesn't have a left child, it doesn't have a right child. What will happen? The execution will go back to its parent. And this means I will need to execute the second child's pre-order operation for this node. So we go to 1, okay? Print it, no left child, no right child, go to the parent. The parent, it doesn't have any more children, so we are done with here. We will go back to the parent. Does it have any other children? Yes, there is 4. This is why you print 4 there. No left children, no right children. Go back to the parent node. Does the parent node have any other child? No. Then we are done. So we will go back to the parent, and this has another child. We continue with this guy, and then we print it there. And for this one, just call the recursion again for its left child. Call the recursion for this left child, right? And then what we have, no left child, no right child. Go to the parent, go to the right child. So print 5, 5 is there. Go to parent, no other children. Go to the parent. I have one more, so I will go to 2 and print it there. Okay, so this is called the pre-order traversal. The difference between the pre-order traversal and the post-order traversal is just one line. Instead of visiting the node, as soon as you land on this node, you postpone it, you postpone the visit operation after you are done with all the children. That means when I start with the root node, I will not perform any action because I have children to be taken care of. So I will go to them. First, I will go to the left. Still, this one has another child. This one has another child. So when I reach 3, okay, so this doesn't have any left child. This doesn't have any right child. So nothing, no children. Since this doesn't have any children, which means I am done with all the children of this node. And what I can do is I can now safely perform the visit. Okay, I will go to the parent. Does the parent have any other child? Yes. That is why we still do not print the parent, but go to the other child. So this is 1. 1 doesn't have any children. So that means this is a final external node. So we print it. We go to the parent. Now, take care. The parent, this node, is done with all of its children. That means now it is safe to print, to perform the visit to that node. So you do it here. Now you are done with this part. You go to the parent, but this parent has another child to be taken care of. So that is why I go to 4. Parent is done. So that means I can safely print it. So that is why you print that operand. Similarly, you keep going that parent, this children, this way, you will reach 9. Okay, and then go to parent, go to right child, it is 5. Go to parent, childs are safe now, so that is why I can print this node. go to the parent. There is one more child there. I will go and print it. Okay, now all of the children are safe. I can just print the parent. It is this one. Once everything is done on the tree other than the root node, you came back to the root node and then you print it. Okay, so this is the post-order traversal. I would like to take your attention to that point. So with the recursion, these are just 2-3 lines of code, post-order and pre-order. Let's do a bit more with the in-order traversal. As I said, in-order traversal is only doable if this is a binary tree. If this is a binary tree, each node has at most 2 children, so left child and right child. What happens, as the name suggests, okay, I will just perform the operations on the left child. When I am done with everything on the left child and its descendants due to the recursion, I will perform the visit operation, then I will go to the right child. So let's do it. I start from the root node, go to left, go to left, go to left. I cannot go any further to the left. So I go back. Now it is the print time for this node, so you just print it, okay? Right child, nothing. You go back. You go back to the parent. Now you are done with the left child of this parent. That is why it is safe to print it now. And you go to the right child. Again, there is no children of this node, so that is why you print it here. You go to the parent, you can print it, then 4, right? Then the root node itself, and then the same story with the 9 minus 5 plus 2. Okay, so this will be those things. But remember, in-order traversal can only be done if this is a binary tree. On the other hand, pre-order and post-order traversals are all valid on general trees. Okay, so what would be a good exercise is to study achieving those pre- and post-order traversals by using stacks. I suggest you to check those operations from the internet if you would like to learn them better. And with this way, you will see why recursion is a very powerful tool. Okay, so without the recursion, implementing a pre-order or post-order traversal by using stacks is a lot more difficult, a lot more messy than doing them with the recursion. Okay, and what would be a nice exercise again? Trying to create the original tree when given some of its pre-order, post-order, in-order traversals. I mean, so the pre-order traversal of this tree is this, and the in-order traversal is given like that. Could you please draw me this tree? Okay. And why we need 2 of them? Because think about that. Is it enough to draw, having just the pre-order or post-order traversal would be enough to create the tree itself? Okay, so someone gives you that, okay, so this is the sequence of my pre-order traversal of this tree. Can you create this original tree? Or let me say, is this original tree unique? Can you have more than one tree that has the same pre-order traversal? However, when you have the pre-order traversal and the in-order traversal, then this will not be possible, right? So I would like you to think about that. Okay. We will just continue quickly with the graph data structure. So graph. The tree data structure, it implements a parent-child relationship. Graph is more general, okay? It is, again, a nonlinear data structure, and every connection between the nodes, they implement a type of relationship. For instance, on this graph shown here, okay, so what we implement is the co-authorship. So these guys have papers written together, okay? Witter has co-authored papers with Amasya, Hollis, Goodrich, and Preprat. Okay, so these are the co-authors of Witter. Okay, so similarly as for the Goldwasser, so who are the co-authors? So it is the Goodrich and the Tamasya, since they have this connection. The difference between the tree and graph is that with the graphs, there might be some cycles. In general, we show a graph with two sets. Okay, so a graph is equal to a combination of two sets. So these are the edges and vertices. Okay. So what is an edge? An edge is the connection between two vertices. These are called, this is a vertex of the graph, this is a vertex of the graph. And the connection between these two vertices is the edge. So this is an edge, this is a vertex, and this is a vertex. Okay. The interesting point with the graphs is actually they may encode many practical real-life scenarios. So it is a common practice in problem solving in real life to model the problem as a graph problem and then going and checking the graph algorithms to see if there are some algorithms already established, already proven to be correct, and we can use them to solve our problem. Okay, so this is a general methodology. We will have a separate lecture in the future on the graph algorithms, mostly the shortest path, minimum spanning tree, such things, and graph traversals as well. So that is why we will not be covering them in this lecture. Okay. So there are many types of graphs. Again, some terminology. If the edges has a direction, we call this a directed graph. If there is no direction, okay, then this is called an undirected graph. Each edge might have a weight on it, then this is called a weighted graph. If there is only one direct connection between two nodes, it's a simple graph. If there are possible connections between two vertices, so this is called a non-simple graph. So this is a dense graph. So that is something important. Okay, so we have edges and vertices, right? How many edges you have and how many vertices you have in a graph? Okay, so actually the maximum number of edges when you are given n vertices might be n times n minus 1 over 2, right? Every vertex might be connected to all others, so that will create that much of edges. That means the number of edges when compared to the vertices, it might be dominant. It might be quadratically more than the number of vertices. If the number of edges is a lot more heavy than the number of vertices, we call this a dense graph. If all vertices are connected to all others, that means a complete graph. If there are no cycles in a graph, so we call this an acyclic graph, and there are some other types of those graphs, okay? But here we should remember how we can represent a graph. To represent a graph, we have mostly three types. Before going to those representations, I would like to talk a little bit about the operations that we have on graphs. You know that's what we call these the abstract data type of a graph. What I can have, what I would like to know when I have a graph. So what is the number of vertices? What is the number of edges? So it would be nice to have those counts ready. I would like to iterate over all vertices for all vertices in this graph, or for all edges in this graph. So it needs iteration through the vertices and edges. So get edge is an extremely important functionality because it tells me that, could you please return me the edge connecting vertices or nodes U and V? Okay, so we need this a lot in algorithms. Degree of a vertex, degree of a node means how many connections it has. Incident edges of a vertex means, okay, so this is a vertex, this is the Goodrich, and who are the incidents of this one? So they are these guys, so these are the incident edges of Goodrich. Surely I may need to insert or remove some edges, some vertices. Given an edge, so let's say this is my edge, which are the endpoints? What are the vertices this edge is connecting? Okay, in this case, this one and this one. So this is another important operation. And these operations are supported with different efficiencies, with different graph representations. One thing we should always remember is this: the performance of graph algorithms mainly depend on how you represent the graph. Sometimes you read something, so I have such and such an algorithm, assuming that the graph is implemented with an adjacency list, assuming that the graph is represented with an adjacency matrix. That is because those operations we visited now has different efficiencies, has different complexities in each representation. So let's visit those representations very quick again. The first one is the edge list. This means, okay, I have a list. This is the list of edges. We are talking about this graph. So what are the edges? E, G, F, and H. So E, F, G, H. So this is my edge list, okay? And what happens is, for each edge, it connects two vertices, two nodes. For instance, that edge E is connecting U and V. So that is why you may assume that I have another list of vertices, and this one has U, V here, okay? In other words, you can say E is connecting U and V. So let's make U much better, okay? And for instance, F, what happens? F is connecting V with W, right? And for G, it is U and W, and the rest. Okay. So this is called the edge list representation. For instance, let's see what would happen. I would like to see if there is an edge connecting U and Z. Actually, there is no edge. However, to understand it, what I need to do is I need to pass over this edge list and check all of them one by one. If I would like to get the AND nodes of F, I should go to the edge list, find F, and read the corresponding AND points. So this is called the edge list representation. Usually, edge list representation is rarely used in practice, so it is a very basic representation. What we see in practical applications a lot are the adjacency lists and adjacency matrix representations. So with the adjacency list, speaking about this specific graph, okay, you see, I have my first node 1, and 1 is connected to 2 and 5. So that is why I have a list 2 and 5. So you may assume this as a linked list, okay? For 2, I have 1, 5, 4, and 3. So they are here. For 3, I have 2 and 4. They are here, right? For 4, I have 5, 2, and 3. And for 5, I have 1, 2, and 4. So this is the adjacency list representation. With the adjacency list representation, for instance, you would like to get the edge connecting 2 with 4, then what you will do is you will go and check the lists. The list devoted for 2, the list devoted for 4. Okay, so you see that 4 is shorter than the list devoted for 2. That is why it is better to work on 4. And I'm curious whether 2 and 4 is connected. I will just pass over this shorter list and see that yes, 2 is there, and I return my answer. Okay, so this is the adjacency list representation. And here is the adjacency matrix representation. With the adjacency matrix, we have a matrix. How many nodes I have? I have 5 nodes here. So that is why this matrix is n by n. You put the vertices here, all vertices. Okay. And if two vertices are connected, then the corresponding position in the matrix will be a 1. 3 is connected to 4. That is why I have 1 here. You see, 3 and 4. This is connected. So that is I have 1 here. On the other hand, 3 is not connected to 5. So 3 is not connected to 5. So that is why you have 0 there. This is a matrix. What is good about the adjacency matrix? You can immediately check the connection between 2 vertices. I will just find the corresponding column and the row, and then I will go and check it. One last point maybe we need to mention: whenever we have the weights on the edges, it is not that much difficult to reflect it on those data structures. Instead of zeros and ones, you can also accommodate the weights with the matrix notation. And for the list, you can just put the weights with the nodes themselves. As I mentioned, so we will be studying the traversal algorithms and some more sophisticated graph algorithms later. This is all I would like to say about the graphs at this time. And I think with this review of tree and graph data structures, we are done with our data structure review for preparation of our main course, algorithm design. On the next lecture, on the next video, we will start with the analysis of algorithms, the efficiency, and further discussions, asymptotic notation, whatever. Okay. Thank you. And hope to see you on the next video. Take care. Bye bye.